Okay, I'll start off with worksheet 4, make sure I cover these two topics. And then if we need to circle back to worksheet 3, we can do that. Okay, so here's the diagram or the chart that helps me progress through problems involving derivative inverse at a point. So a visual perspective is this. Imagine you had a function where you had two expressions or that were inverses of each other. So that just means graphs that imagine it just a mirror image over the line y equals x. So the idea is that we're asked to find the slope of the graph at this point. But all the information that's provided for us are on the function side of things. So we're going to have to know how to maneuver our way around. If they give us the x value, then we have to understand that the order pair on the inverse function is going to be the corresponding version of it on the original function. So a function and its inverse, they're always going to have flip-flop versions of their order pairs. So if there's an order pair a comma b on the inverse, there must be an order pair of b comma a. And because everything is stored on the function side, we're going to have to find the derivative. From the derivative, we can find the slope. Once we find the slope, then there's a very specific relationship between the slope of this tangent line versus the slope of this tangent line. And you can tell that one is steeper than the other, but they're both going to be the same sign. They're both, if one is positive, the other is positive as well. So the relationship is that whatever slope that is found on the function side of things, then it's always going to be the reciprocal on the inverse side of things. So if this is a slope of 8, then this slope over here is going to be 1 over 8. So we're really not doing anything on the inverse side of things. We're doing everything on the function side of things. And because we understand the relationship, we're able to make some conclusions based off of information that we found on the function side of things. Okay, so let's go into number 1 to kind of talk about minus x. So I have a function x cubed minus x plus 2, but the information that they give us is on the inverse side of things, and they give us the x value of the inverse. So I like to create this chart. This chart, basically, the first row gives me the relationship between the order pairs, between the function and the inverse. And the second row is going to show that relationship in terms of the slope at their corresponding points. So basically what we're going to do is we're going to start here, gather information, and we're going to work our way around this chart. And by the time we come back around, we're going to have enough information to finish off what we're looking for. So I'm trying to find f inverse prime at 2. I'm going to start making my way around this chart. Right? I know that this is the x value of my inverse. But we know that there's a very specific relationship between the order pair of the inverse and the order pair of the original. It looks like we don't have the full x and y value, but we do know if the x value of the inverse is 2, then 2 must be the what? The y value, right? So even though we don't know anything else about this problem, even though we haven't even touched this function yet, we should be able to always get to this point just by that 2, right? That 2 is going to carry all the way over to this side here. And now we can do some investigation in terms of, all right, what information do I need to find? I need to find this value so that I can find the derivative at that point. So to find this x value, I'm going to go to my function and I'm going to realize that, well, I have the y value. So I'm going to insert that 2 into the y value location of my function and work backwards and solve for x. If I can solve for x, then I can continue moving forward. Okay, so sometimes we have to do a little bit of guess and check, but in this case, I think we can solve it without algebraically, without running into too much trouble. So I'm just going to, if I subtract the 2's, I can get the number to go away. I'm just left with 0. But the strange thing here is that we actually have multiple solutions. So let's find all the solutions and then, because usually we just have one x value, but in this case, looks like as we factor, we're going to have more than one here. This is a difference of squares. Okay, so I'm going to solve for x. Looks like I have 3 solutions, right? X equals what? X could be equal to 0, -1, and 1, right? So this is a little bit strange because we usually just get down to one solution, but we can test all of them and then just see which one shows up in the answer choice, right? So it could be 0, it could be -1, it could be 1. Okay, I'll leave that alone for now. But ultimately, I know I have to find the derivative at one of these points, and that's going to lead me to a slope. And I know that this numeric slope is going to lead me to the slope over here. So I know I have to work my way down to the f prime. So let me find f prime. So f prime is power rule. So x cubed becomes 3x squared, minus x becomes -1. So I have 3 variations here. I just want to be able to go through all of them so that whatever shows up in the answer choice is going to be the one that I choose. So I need to evaluate f prime of 0, which is 3 times 0 squared minus 1, which is -1. I need to find f prime of -1. -1 in for x. I get 3 times 1 squared minus 1. That's 3 minus 1 is 2. And if I find f prime of +1, 3 times 1 squared is 3, minus 1 is also 2. So it could be either -1, 2, or 2, and these are just the same numbers. And I know that whatever slope I find on the f side, what's the relationship on the inverse side? Yeah, just flip it, right? So -1/1 is still -1. This becomes 1/2, and this is 1/2. So our answer should be either -1 or 1/2, just depending on what shows up. And looks like 1/2 is going to be our answer choice that shows up. Yeah, typically we don't see a lot of questions like these where you have multiple x values and you have to kind of test them out to see which one is the one that actually shows up on the list. But the process is the same, right? You go through the same process for all these problems. Okay, let's go through number 2. Yeah, some of these problems will get easier in terms of the setup here. So let's look at number 2. let f and g be differentiable everywhere. G is the inverse of f. So this will be easier because we don't have to do any calculus. We just have to kind of work our way around this chart. Right. I'm looking for g prime of 3. G and f are inverses. Right. From here, I'm just going to work my way around. I know that 3 is the x value of my g function, which must also mean it's the y value of its inverse. Right, so we should be able to do this even without looking at the rest of what's given to us. So this problem is actually makes it easier because they already give us the y value, so we can just fill those in. We know this is 4, we know this is 4, and ultimately, if I can just find f prime of 4, then whatever I get as my slope, it's going to lead me directly to the slope on the g side. Okay. F prime of 4, conveniently, they just give that to us. So g prime of 3 must be what? Yeah. I'll skip number 3 because 3 is similar to this one, and you guys can try that on your own. But I want to do number 4. Number 4 does require a bit more steps on our side. So let's look at number 4. Any questions with 2? Okay. Okay, so here's number 4. Okay, so we're looking for the derivative of inverse at a point. So again, I like to use the chart to help me map my progress. So we should always be able to fill this in without looking at any other parts of the problem, right? Okay, so I know that I don't have anything on the inverse side. I do have my functions, so I'm going to make that connection. Well, I know the y value of my f of x, so I'm just going to insert that into here and see if I can get to my order pair. Okay, subtract 1 from both sides. Natural log of what is equal to 1. We could raise both sides with e as the base. We know this will go away to just be x. E to the first power is just e. X equals e. Okay, so there's our entryway into our moving forward in our problem. I know that my order pair is e comma 2. So I know that my inverse must be 2 comma e. That means if I can find f prime of e, then that will lead me directly to the slope that the problem is asking for me to find. So I want to find f prime of e, but before I can find f prime of e, I have to first find f prime of x. Okay, what's f prime of x?
It'd be 1 over x.
Good, yeah. 1 goes to 0. Natural log of x is u prime over u. So f prime of e is just what? Yeah, 1 over e. So if the slope of the f graph is 1 over e, then the inverse must be just e, right? Take that 1 over e and flip it. All right, good. All right. Okay, let's do some linear approximation. No questions? So linear approximation. Basically, it's just finding tangent line. If you can get to the tangent line equation, you've done all the work, and the rest is just plugging in. But if you just think of linear approximation as, okay, I just need to find the tangent line, then that just simplifies a lot of, don't have to worry about anything else if you can just get to that tangent line. That's where all the work is involved. Okay, so let me go through the steps. Linear approximation, we identify the ordered pair, we identify the slope, and then we get to our tangent line equation, point slope form. Once you can get your tangent line equation in point slope form, then all that's left to do is the approximation portion of our step, which is just dumping that decimal value into your tangent line. Okay, so here's number 5. Here's our function. We know our decimal is, so whatever decimal they give you, that's not going to be the first thing you do. That's the very last thing that you do. Right. The first thing that you do is going to find the tangent line equation. Tangent line equation is going to be revolved around a whole number for the x value at least. Maybe the y value, maybe something different, but the x value will always give you a nice whole number for your x value. Okay, first things first, we want to find the ordered pair. So I know my ordered pair has an x value of 0, but I don't know the y value.
Why do you 0 and not -0?
The negative 0.01 is for the approximation step. We're going to create the tangent line first, and then the decimal is what we're going to dump into the original expression. So that's where the approximation comes in. The approximation is where the decimal comes into play, but we never do that until we actually have an equation to work with. Yeah, so anytime you see a decimal, that's the very last thing that you touch. You don't touch that at the beginning. Okay, so how can I find my ordered pair? What do you guys think? Yep, just plug it in. So 0 in for sine of x. Sine of 0 is 0. Square root of 1 is 1. So there's our y value. Okay, we also need to find the slope. But to find the slope, we have to find what?
Would it be the derivative?
Yep, we got to find the derivative, right? Got to find y prime. So to find y prime, we first have to make sure we have everything set up. Let me rewrite it in a form that's easier to work with. 1 minus sine x to the 1/2. So if I want to find y prime, what method is involved here? You see what's involved in my method to finding derivative?
Maybe chain rule?
Yep, good, chain rule. So chain rule, we know there's an outside we got to worry about. We got to worry about the inside portion, and we're going to take turns with each derivative.
Why do we need the derivative for the equation?
Because we need to find the slope. We need to create our tangent line equation. So tangent line equation requires order pair and slope, so slope's going to come from your derivative. Yeah. All right, so chain rule, y prime. We'll take care of the outer portion first. There's a power rule going on with the parentheses. We fill in the parentheses with the original because we're not ready for that portion yet. So once we take care of the outside function's derivative, then we're worried, then we can focus in on the inside. One's derivative is 0. The negative sine of x becomes negative cosine. The sign doesn't change. I mean, the negative, yeah, sine just becomes a positive cosine, but the negative is going to stay with it. So once we have our derivative, you can clean this up or you don't have to, but we're going to be evaluating the slope at 0, right? Now, I know this looks really messy, but it's going to clean up nicely. Sine of 0 is 0. 1 raised to negative 1/2. That's really just going to be 1, so that's nice. That negative 1/2 is not going to have any impact. So it's just 1/2 times 1 times, and then cosine of 0 is 1 as well, so negative 1. So 1/2 times 1 times negative 1 is negative 1/2. Okay, so most of our work is just trying to get that slope. Basically, we're just doing tangent line equation. All right, so now we have an order pair, now we have our slope, now we can build our tangent line equation. Order pair, slope, point slope form. Solve for y. So now that you've found your tangent line equation, there's one more step, and that is the linear approximation portion. Now you can play with the decimal, and that decimal is just going to be inserted into your tangent line equation. Okay, clean all that up. You should get 1.05. Did you get that? Nolan, did you get that?
Yeah.
Okay. All right, how'd you guys do? Any questions so far? Number 6 and 7. 6 is a easier version of 5. 7 is even easier because you can just, they give you order paired, they give you slope, and you just tell them the point slope form. So number 8 is another chain rule problem, requires a bit more work. So let's do number 8. Okay, so the first thing we want to do is just focus our attention on the order pair and the whole number. The decimal, remember, any decimal value is always the very last piece. It's the approximation portion of it, not the, we don't use that value to create our tangent line equation. Okay, same idea. We want to find our order pair. Use the original function to get to your y value. E to the 0 is 1, 1 plus 3 is 4, root 4 is 2. Next up, we have to find our slope. Slope comes from the derivative. And again, with the derivative, we have to rely on what method? Chain rule, yeah. Okay, give you guys a chance to practice that on your own, and I'll follow up. Try that. See if you can get the full derivative on your own. Okay, Nolan, what you got?
I got 1/2 plus GDX to the negative 1/2.
Okay, let's the first part you got right. Now we got to worry about the inside portion. 3 goes to 0, but what's the derivative of e to the x?
Oh, e to the x times 1.
There we go. Yeah. So basically just e to the x, right? But yeah, technically, if you want to do that times 1, you can think of it as e to the u times u prime. Yeah. So now we have our derivative. We can use the derivative to find our slope. Enter 0 in. But here, I think I may want to do a little bit of cleanup before I enter in 0, maybe a little cleaner here. Okay, replace 0 in for x. E to the 0 is 1. 3 plus e to the 0, that's 4. 4 to the 1/2 is 2. 2 times 2 is 4, so did you get 1/4 as your slope? Okay, so we have our ordered pair, we have our slope. Now we can do point slope form. Solve for y, and then our final step is working that decimal. One-fourth times 1/4 is 1/16 plus 2. Answer choice B. Okay, any questions with worksheet 4? Okay, so I inserted some of these problems into tomorrow's worksheet, so you'll get some more practice with it on tomorrow's worksheet. Let's use the remaining 15-20 minutes. Let's pick at some of the problems from worksheet 3. So
I have one question about the setting, something class.
okay.
I'm just wondering, what the x is greater than 0.
Oh yeah. No. Yeah, that's just for them to ensure that we're not going to get a 0 out of this. Because if it's equal to 0, then it's possible that you may have an integral from 0 to 0, which is 0. So they want to ensure that one of these answer choices is going to stand. So they just have to make that statement. Okay, so I skipped a lot of the third page from worksheet 3. So maybe we can do some of the problems from worksheet 3. Okay, it says if f is continuous, f prime equals f of x. Okay, so this tells us there's that relationship, right? That this f function, that this f function that we see in front of us is really sitting at the uppercase f prime level. Okay, so we want to get everything in terms of f, but we need to recognize that, okay, this is going to be a u substitution problem. And what do you think the u value is going to be? Yep, whether it's inside that parentheses, okay? Well, that's the thing. With u substitution, we're going to save that bottom for the derivative to handle. All right. So we're just going to let that u value be the top. Okay, so. All right, we'll go through u substitution. going to underline the pieces that we're going to handle first, and then we'll let the dust settle and figure out what to go from there. Square root of x, same thing as x to the 1/2. I can go through power rule there. Do a little bit of cleanup. Push that that x back to the bottom. I'll make it back to square root. And if I cross multiply, I can get that dx by itself. Okay, so there's my substitution for dx, right? Leave the bounds out of it because we're doing u substitution. So f of u over the square root of x times, replace the 2 root x du and for dx because they're equal. Okay, so what do you notice here? Mm-hmm. Yeah, move the 2 out front. Okay, so we're left with 2 integral of f of u du. And now this is something clean because we have a rule that can handle this because the problem says f uppercase f prime equals f. So that means if I take the antiderivative of lowercase f, it's going to bring me up to uppercase f. So we don't do power rule. We just go through first theorem application. So we know 2 lowercase f is going to turn to 2 uppercase f. But hold on, let's look at the answer choice here. Okay, so we have to evaluate our bounds. Okay, we have to evaluate our bounds. We have 2 options here. Either we can convert the 1 and 4 in terms of u, or we can bring this back in terms of x and then use 1 and 4.
I like that.
Okay, that's good. What we don't want to do is we don't want to use this u and the 1 and 4. That's the mistake I see students make because right now the 1 and 4 is mismatched with that u. So yeah, let's bring it back. I like to do it this way too, especially if they're not forcing us to do it in multiple choice. So I'll bring the u back in terms of x. U is equal to root x. Okay, now I'm ready for my 1 and 4. Okay, upper bound first, 4 info root x. Minus, then lower bound, 1 info root x. We can clean this up a little bit. Root 4 is 2. Root 1 is just 1. Answer choice A. Let's see. Okay, let's do, we'll skip 10 and 11. I think 10 and 11, it's like number 8. If you understand the formula, you can just plug it in and there's not, oh wait, is there anything strange about number 10? Oh yeah, I do want to point out something about number 10. So number 10, it says particle moves along the y-axis, so that its velocity is given by v of t. Position is 4 at time t equals 0. What's the position of the particle when its velocity is first equal to 0? So this is definitely the formula that we talked about with number 8, a variation of it. Final position is equal to initial position plus displacement of the velocity. But they don't tell us explicitly where that position is. So we actually have to set velocity equal to 0 and figure out that t value for our b. So what you would have to do is, because normally we will say x of b equals x of a plus integral from a to b, but we don't know what that b value is. We have to figure out where that final location is. So we actually had to set velocity equal to 0, use the calculator, graph it, find that x-intercept, and that x-intercept being is 1.379. Once you have that value, then it becomes straightforward. Then you just do x of b equals x of a plus the integral from a to b of v of t. Sometimes the problem makes it a little bit more involved, where you got to do a little bit of work where they don't give that value to you. You got to find it. Okay, but it's on the key, so try that, and if you get stuck, see if the key will help you out. 11, I think, is straightforward. 11 is straightforward. Okay, so let's look at number 12 and 13. Okay, so now they're telling you what to use for substitution. Okay, so this ends up being, yeah, we'll see. There's a little bit of messiness involved here. Well, it's just a little bit of additional step here. So here's number 12. So they're telling us to go through use substitutions. So, oops, I wrote out the problem wrong. Oh yeah, that's right. Okay. I need to replace root x. I need to replace dx. Let's see where we are. Okay, so if I want to find the derivative, du dx equals
dx is 1/2 x or 1/2x.
Yeah, so we see that there's going to be that leftover root x that's not taken care of, right? We may have to do a little bit of playing around here to get that, to figure out a way to get that to work out. Okay, cross multiply to get that dx by itself. Make my substitutions. All right, so there's an issue, right? The issue is that I'm not truly doing U substitution until every x is resolved, and we don't see a way to cancel this root x out. So even though the root x can't go away, maybe we can rearrange it or find a way to get that root x to be represented in terms of u. So this is, we got to resolve this, right? So how do you think we can take care of that root x? Yeah, that's probably more work than we need to do. Do you see, is there something that we can replace root x with? Yeah. We know they're equivalent, so we can just go ahead and replace that root x with u. Okay. But if you look at the answer choices do not have, it's not asking for us to solve. It's just asking us to set everything up in terms of u. So I think they're making it easy on us because all the bounds are the same. But let's pretend like we're not able to see the answer choices. How would you adjust the bounds so that we can get everything lined up in terms of u? Can we use the 0 and 9?
Don't you plug them in for x or something like
Yeah, plug it in for x and we convert in terms of u. So normally we would want to just convert everything to be in terms of x, but because our answer choices are in terms of this integral, we're kind of forced to have to go through changing the bounds. So our conversion is root x. So we know that if x equals 0, then because u equals root x, u is root 0, which is 0. If x equals 9, then u is equal to root 9, and root 9 is 3. So we should be able to replace 0 and 3. If I want to pull the 2 out in front, I think this will match your answer choice better. A.
Mr. Yang,
Yes.
why exactly did we have to change the bounds?
The reason why is because if we didn't change the bounds, then there's a mismatch then, right? If I put 0 and 9 here, then that doesn't make sense because my variable here is in terms of u, but then my bounds are in terms of x, and we can't have that.
Okay, that makes sense. Thank you.
Yeah. So I think this problem is nice in the sense that they didn't change the bounds at all, but they could have made things more difficult or just more of a trap if they had one of these being 0 to 9, right? And I think we gotta be careful about that. Right? Not all the answer choices on problems will be as nice as that, where the bounds are all the same. You have to make a decision there. Good. Any other questions with 12? All right, so let's do one last one. We'll do a differential equation, number 13. Order pair, 0, negative natural log. All right, so we're going to go through all the steps like we've done before with differential equations. We're going to try to clean this up, separate the variables, cross multiply if we need to. Eventually want to isolate all the y's on the left, all the x's on the right. Once we get full separation, then we take the antiderivative. And then once we find the antiderivative, a plus c will show up. We can solve for c, update the equation, and then solve for y. So the first thing I see is, okay, it's going to be a lot easier for me to work with this if I can split this up into each individual component. So we're going to rewrite this as e to the y times e to the x. And while I'm doing that, I'm also going to force this into a fraction so I can just cross multiply. Separation of variables may not be complete after I cross multiply, but it will get my dy and dx's in their right places. Okay, so it's good. It's a good sign. Dy, dx, they're ready to go. There's no need to move them anymore. But do we have full separation yet? Okay. What needs? Yeah, that e to the y needs to be moved over to the left, but that's the only thing that needs to move, right? Just that e to the y. All right, I moved that over, I split it up, I got 1 over e to the y dy equals integral of e to the x dx. Am I ready to approach with integral rules?
I think so.
This work for you for one lot.
Say it again?
This is the work for you for one lot.
Oh, bring it back in terms of u. Yes, but there's something though. Can you? Yeah, the right. I'll tell you this. The right side is ready, but the left side.
Do we have to bring the e to the y up to the numerator?
Yeah, this is not the proper location, right? So if you look at your formula sheet, look at the formula sheet for the integral. We have an integral rule for e to the u, right? And that matches nicely with this, so we know that this is just going to be itself. But we don't have a rule for 1 over e to the y. So we have to force this into this format before we can apply an integral rule. So we got to bring that e up, and if we bring that e up, that y is going to change sign, and that's going to force a u substitution into our problem. Yeah, so a little bit of extra work on that left side required. Now we can go through u substitution, and we're going to have to deal with a negative that's going to come out of it. Okay, let me shift this up. Okay, I'm not taking the integral yet. I want to just leave both sides at the same level, and I'll take the integral all at once. Okay, so now we're ready. We can just push that negative out in front, and then we can do the integral of both sides. E to the u becomes e to the u, e to the x becomes e to the x. The negative just kind of hangs out. Plus c. Okay. We have the antiderivative, we have our general equation. Let's bring the u back in terms of our original variable. All right, any questions so far? I just want to have this in the maybe easier way to look at it. I like to work with something in terms of positive exponent. So I'm just going to bring that e back down, because now I know the rest of it is just algebraic. I don't have to have this e up to the numerator anymore. The calculus is already done. So I can either solve for y first, or I can solve for c. Maybe it's easier to solve for c first because, I don't know, this feels a little messy having to keep track of that c, and that e is such a weird place. So I'm going to solve for c first. Okay, there's my order pair. 0, negative ln 4. So I'm going to solve for c at this point. Okay, 0 in for x, negative natural log of 4 in for y. Actually, you know what? I think it may be better just to leave it in the numerator, because the two negatives are going to cancel out each other. So I think that's, yeah, I shouldn't have brought that down. So I'm going to go back and I'm going to, it's going to be a little cleaner this way. Things will have to come back up anyway. So I'm just going to leave this in that form. Go ahead and insert that negative natural log of 4 in for y, and the two negatives will cancel out, and then I'll be a lot cleaner rather than moving it down. Two negatives cancel out. Now we know that e and natural log have a way of canceling each other out. We know this just dropped to be 4 with a negative hanging out in front of it. So negative 4 is equal to, we know e to the 0 is 1. Subtract 1 from both sides, c equals negative 5. Right, so now that I have my c value, I'm going to go back to where I initially made my substitutions and then try to get y by itself. Okay, I want to solve for y, but one thing at a time. I'm going to get that negative over to the right side, multiply everything through by negative 1. All right, what do you think we can do to get that y to come down? Natural log, yeah. That negative e is now free to move. Sorry, negative y is free to move. gonna rearrange this. I just like, if I have a choice, I like the positive term to come first. And I think that matches with their answer. Maybe it doesn't. Okay, final step. Well, we know natural log of e is just 1, so we can make that drop out. Move the negative over. Okay, sorry. So I guess the answer choice does not have the positive term first, but I just like to write it with the positive term. Oh, so here's a kind of a strategy point, is that you know, on my exam, on my test, there's only 8 questions, 30 minutes. You're gonna have time to do this. But on the AP exam, if this was on the non-calculated portion, you only have 60 minutes to do 30 problems. That means you only have 2 minutes per problem. So even though you may be at this problem and you're like, I know how to do this. Even though you know how to do this problem, it may not be worth your effort to spend all that time on this, if that makes any sense. So what I mean by that is, this is a good problem to do, but don't do this problem at the cost of 3 other easier problems that take a little bit less time. So if you get to a differential equation, what I would do is wait until the end. Make sure you do all the easy stuff first, and then spend the rest of your time on the ones that you know how to do, but just takes a long time. Save that for the end. Okay. All right, thanks, guys. I'll see you guys tomorrow, and I'll have a help session tomorrow afternoon and Wednesday afternoon. All right, take care.
Thank you, Mr. Yang.
See you guys. Bye.
Thanks, Mr. Yang. Have a good day.
You too. Have a good day.